Welcome to those here on campus and to those who are joining our live stream. Welcome, this is Saturday Morning Physics, and this is our very first presentation of 2025. We've been away for a while, and we're thrilled to be back. I'm Physics Professor Tim Chupp, one of the organizers of Saturday Morning Physics, along with our team, which includes Carol Raybuck, who greets everyone and is essential in organizing this, and Monica Wood, and her staff at the Warren M. Smith Demo Lab. And today we want to give a special shout out to Sean Rice, who's a Michigan robotics research technician who's here, who brought this robot, which you'll hear about today. Before moving on to our program, I want to remind you that Saturday Morning Physics is made possible by you and by your many generous contributions to Saturday Morning Physics and for being fans. Thank you so much. And thanks so much for making Saturday Morning Physics sustainable so that we can continue to bring you cutting-edge science topics, topics about the intersection of science with policy and our everyday lives, and many, many other things in addition to physics. We've put together an exciting program for the spring. Yeah, spring. It's coming. And today we'll learn about robots, and coming up there are talks on quantum materials. We have a family-friendly audience participation, hands-on event that is student-led, and it's coming up on March 15th. We call it the Extravaganza, which we've practiced pronouncing many, many times. You can find more information about that in a flyer in the back, and there's much more. So for more about supporting us and more about our program, go to SaturdayMorningPhysics.org. Before moving on, I want to note that today's event will conclude with a question and answer period, which is traditional. And for those who are joining us online, and in fact for those who are here, you can either ask questions live in the room, or you can send your questions to physics@umich.edu. Now, we're deeply honored to welcome to Saturday Morning Physics to the stage Oluwami Dosunmu-Ogunbi. Wami. I did that okay? That wasn't for me, I know that. She's a visiting professor of mechanical engineering at the Rose-Hulman Institute of Technology in Terre Haute, Indiana. And actually, we're welcoming Wami back to Ann Arbor and to the university. In 2024, she received her PhD in robotics, the first black woman to do so here at the University of Michigan. And she will start as assistant professor at Northern Ohio University in the fall. Wami grew up in Montgomery, Alabama, and she did her undergrad studies at the University of Illinois at Urbana-Champaign, finishing with a degree in mechanical engineering in 2017. And then she came to Michigan to do research with Jess Grizzle and Chris Jenkins? Chad Jenkins, thank you, in the mechanical engineering department on bipedal robots. And it sounds very straightforward, this path, but it wasn't, especially for someone who doesn't look like an engineer. Think of the stadium of pocket-protected, narrow-tied, crew-cut engineers that NASA likes to show in publicity photos of the Apollo program. Wami's journey is an inspiration, and she is dedicated to inspiring and teaching future generations, both by developing the science and engineering curriculum and by inspiring resilience and perseverance in young people pursuing an academic path. She's an admired and decorated speaker, and her venues have included TED Talks, and she was a student commencement speaker last May at the 2024 Michigan Stadium commencement, as well as at the engineering graduate commencement. I could go on, but you're not here to hear me talk. You're here to hear Oluwami. So welcome back, and thanks so much for joining Saturday Morning Physics and for your presentation, Breaking Bias, Building Bots, the Intersection of DEI and Robotics.
Thank you. Well, thank you, and thank you, Tim, for that lovely introduction, and thank you, everyone, for taking time of your Saturday to come hear me talk. It is great to be back in Ann Arbor. If you couldn't tell by the picture and the introduction that Tim just gave, I am indeed a Michigan alum, so it's great to be back here on campus. So I'm hoping to be able to tell you about Breaking Bias, Building Bots, the Intersection of DEI and Robotics. What does robotics have to do with social issues? Well, I'm hoping that by the end of this talk, you'll have a better idea of what that might entail. So let's talk robotics. How do roboticists solve very complicated robotics problems? I think the best way for me to illustrate this example is to introduce an example. So let me introduce two robots. We have the Cassie robot and, let me shimmy over here, the Digit robot right here. I literally had Sean bring out Digit only for this part. I am so sorry, Sean, but thank you so much for this effort. But yes, we have two robots, the Cassie robot and the Digit robot, both built by the company Agility Robotics. So I'm going to use these as my example. So the Cassie robot is in need of some help. It is somehow got stuck in the middle of Central Park, and we need to help Cassie get back to its dear old friend, Digit. Don't tell Cassie that I actually brought Digit over here. Anyways, yes, so we need to get Cassie back to its friend Digit. Somewhere in Central Park, and I made out a little map. Cassie somewhere in the upper right-hand corner, Digit somewhere in the lower left-hand corner, so we need to figure out how to reunite these two robots. So how do we do that? Well, roboticists kind of think of programs for building robots in three main domains. One is sensing, then there's reasoning, and then there's acting. Sensing is how does the robot perceive its world? So in the case of this example, we need to be able to have Cassie be able to perceive its environment, see what objects are in front of it, and be able to build a map, essentially. So actually, I can come back over to Digit because it's here, why not? So there's a couple of ways that one can see its environment. So we have here a LiDAR sensor, and in fact, that bigger video that you see on the screen is a LiDAR image. So how a LiDAR operates is that it shoots out a bunch of lasers, and then and measures the distance between whatever surface it reflects off of and wherever the robot is. So you can kind of see how, with that, how LiDAR works. You can see a swing set, there's some buildings, and if you're really paying attention, you'll notice that this is actually on North Campus. In the lower-hand corner, there's a video of just a regular camera data, and what roboticists would use might be not just one type of sensor, but maybe multiple sensors, and then fuse the data together. So all that forms the sensing domain. Then we have reasoning, and so this is how does the robot think? In this case, for this example, we need to figure out how to get Cassie from point A to point B, where it's at right now, to wherever its friend Digit is at. So how do we do that? Well, you can't necessarily take a straight line because we're in a park, there's trees, there's a giant lake in the middle, there's people, there's dogs. So we have to use an algorithm to be able to make sure that it avoids obstacles and doesn't actually end up hurting people in its process to get from point A to B. A good algorithm would also probably be able to update its the path in real time. So as Cassie's making its way through the park, maybe some person walks in front of the robot, maybe a dog starts chasing after Cassie. So a really good algorithm would be able to take in that new information and be able to update the path so that it can continue on to its journey to Digit. So that is the reasoning domain. And then finally, we have the acting domain. And now when I say acting, I'm not like thinking about like dramatic acting. So like Cassie's not going to start like quoting Shakespeare or something, you know, like to be or not to be. Yeah, no, we're not doing any of that, no. When I say acting, I mean moving the robot. So since we're talking about bipedal robots or two-legged robots, this is referring to walking the robot. But obviously not all robots are walking robots or bipedal robots. Some robots are literally just like arms. So the acting behavior here would be like just like maybe picking a block up and then placing it somewhere else. There's also like wheeled robots. So the acting movement here would be just like driving those wheels to get from one point to another point. Fun fact, these videos, the one with the arm and the one with the bot, that came from the Robotics 550 course here on campus. So hence me dancing and waving at the camera. We finally got our algorithm to work for the first time. It was great, great day. Yeah. So we have these 3 domains, and each of these domains, as you can imagine, are like quite huge. One can spend multiple PhDs in any one of these domains. I'm personally biased towards the acting domain because that's where my specialties lies in. So I'm going to focus on that for a good chunk of this talk. So let's talk about the acting domain. And here I'm going to bring up 3 more categories because I just like 3s. It's a good number. So I'm going to talk about modeling and then designing constraints and then end with feedback controllers. So what is a model? This is essentially like the digital twin of the robot. So you need to be able to build like this virtual mathematical representation of the robot for the purpose of being able to design an algorithm to move that model, which thereby moves the actual physical robot. So meet Cassie again. We have this robot. It has 10 actuators, 5 on each leg, and each leg is 7 degrees of freedom. And if you're curious, this is like the entire what we call generalized coordinate vector of the Cassie robot. Cassie is actually 20 degrees of freedom, which means it can basically move in like kind of like 20 different ways. It's like a very crude way of explaining it. And then the first 6 are referring to what's called the floating base coordinates. Don't worry too much about that. But I did want to point out these passive joints that I'm going to talk a little bit about later on. So Cassie has these passive joints attached to it. So yeah, with bipedal robots, we can't just use actually one model to represent the system. We need to use multiple models. And that is what we call a hybrid system. So in the case for Cassie or for a walking robot, the first domain or first model would be representing the right leg in the air. So let's say we're trying to walk upstairs. So we have Cassie, it's walking up. And right as that leg is about to touch the ground, then we end that first domain, and then when we impact the ground, that enters the second domain. So those are 2 different models that we need to represent that robot. And then since we have 2 legs here, we have to repeat this on the other side. So now there's another model representing that left leg in the air, and then right before it touches the ground, then we end that dynamics and enter the last domain when the left leg is actually touching the ground. So so now we have 4 models essentially to represent this robot that is walking. And then we can just like cycle through these models as we're trying to walk through a step or go through a step. So let's focus on one of these domains, the continuous domain on like say like the right leg. I'm going to use what's called the floating Euler-Lagrange approach, which is like just a fancy way of saying like I'm just going to generate an equation to represent my robot. And so all the roboticists in the room are going to be like, oh yes, I know those equations. You've probably seen some version of these equations. Everyone else, that's absolutely fine if you haven't seen these. What I did want to point out is that this might look like a relatively like simple equation for like such a complicated robot, but I don't want you to be fooled, because this one line of equations is actually not as simple as it might seem. So, or maybe it doesn't look simple, I don't know. I personally, when I first saw this, I was like, it can't be that bad. It's just like one line, that's fine. But I want to prove you wrong. So let's look at just the mass inertia matrix, which is this first matrix right here, the D matrix that arrow is pointing to. And let's look at it for the 3-link walker, which is that robot right there. It's like a planar robot, meaning it's 2-dimensional, and it's only 5 degrees of freedom. So we're just looking at that D matrix. What does it look like in Times New Roman 10-point font in Microsoft Word? It looks like this. And actually, I can derive this by hand. It's not too bad, relatively speaking. I'm not going to be happy about it, but sure, I can derive this by hand. Yeah. So, okay, let's get a little bit more complicated. What about the 5-link walker, also known as the rabbit model? So if I were to write just that D matrix in Times New Roman 10-point font in Microsoft Word, it looks like that. Almost 5 pages. Yeah, you couldn't pay me to derive that by hand. I would not, absolutely not, no. Yeah, so that begs the question, what about the Cassie robot? Oh, I guess I didn't mention, for the 5-link walker, this is a 7-degree of freedom robot, and it's planar, meaning it's 2-dimensional. Cassie is 3-dimensional, and it is 20 degrees of freedom. Anyone want to guess what just the D matrix would look like in Times New Roman 10-point font in Microsoft Word? Just start shouting out answers. I heard a lot. I heard like 800 pages. 300. I heard, wait, what is that? A book, like a novel. One could write a novel in Cassie. I like that. Okay, I love these answers. Well, Cassie is saying, oh, it can't be that bad. It is that bad. Yes, you could definitely write a book. That I actually crashed Microsoft Word several times just trying to copy and paste it into Microsoft Word. It was a nightmare. And so yes, it ends up being hundreds of pages just to write one matrix down in Times New Roman 10-point font in Microsoft Word. So yes, Cassie is quite the complicated robot. So again, as I bring back these what's called the robot equations, again, don't be fooled by how, like simple these equations might look. Simple is not a good word for it. It looks, I don't know, I'm not good at, I need a thesaurus. Yeah, so now that we have a model of our system, now we can think about, okay, how do we design a constraint? Well, this actually kind of ties a little bit into models of the systems too, because there's 2 different types of constraints. One is known as the physical constraint, which, as the name kind of implies, these are like the physical limitations of the robot itself. So you can think about gears, belts, levers. I have a picture here of Cassie, and you can see these bars that are linking one part of the robot to the other. So it's actually linking some actuated or joints that have motors on it to those unactuated joints. So these are those passive joints that do not have a motor on it. So by moving these joints that have the motors, you're also moving these joints that don't have motors. So that's an example of a physical constraint on the Cassie robot. There's also what's called virtual constraints. So as its name implies, these are these constraints that aren't physically tied to the robot. We virtually impose them by using a controller. So what I mean, so here's an example. We like to represent bipedal robots or 2-legged robots as what's called an inverted pendulum. So basically, if you draw a line from the robot's stance foot, or the foot that is on the ground, to the robot's center of gravity, also known as you can think of it's where the average of its mass is a good way of thinking about it. So you can draw a line from that stance foot to the center of gravity. That forms the inverted pendulum that we're trying to control. And a virtual constraint that I could use is let's make that line, that inverted pendulum, let's make that angle a certain value. So that is one way one can impose a virtual constraint. So here's another way of showing that same thing. I have that inverted pendulum, that's that line from the stance lead to the center of gravity, and I'm trying to make that theta, that angle, be a certain value. And by imposing that constraint, I am thereby making all those joints connected to that constraint. So the knee, the hip, all that, I'm making those also adhere to certain values in order to maintain that angle of the inverted pendulum. So here's another, I guess, visual representation. So here we have the Marlowe robot, where essentially what we're doing, we're making that inverted pendulum angle be just oscillate from side to side. And you can see how this results in the robot stepping forward and backwards. This is also like a function of like, the physical constraints of the robot. Because of course there's like all these links, all these gears. So between the physical constraints and the virtual constraints, it's causing this robot to move forward and backwards. Now, I don't want to show too many equations. I know I showed one. This one's slightly simpler, and I promise it's not too bad. So let's walk through this one. So I have one variable, h0. These are the variables that I want to control and their actual values of what they are. hd is the desired trajectory that I want those variables to follow. And the goal is, or actually I should point out, for HD, there's like, it's a function of some sort of like timing variable or gate phase. But what I want to point out here is that I want to make those variables that I want to control to be as close to those desired trajectories as possible. So essentially, I want H0 minus HD to be as close to 0 as possible. And that is the goal or the objective of what's called the feedback controller. So that brings me to feedback controllers. Yeah, this is actually where I got my dissertation on, so this is what I'm excited about. So feedback controllers. There's so many different controllers out there, depending on like what robot you're working with, what acting movement that you want to do. So I have here just like several videos of what we've done in the lab and beyond. So my personal favorite is the one in the top left-hand corner. Sorry, I forget my left from right. So top left-hand corner, that was like one of the last videos that I was able to make before I left Michigan, because that's like one of the final videos for my dissertation. So we have Cassie walking through sand, gravel, and rocks. Next to that, we have a video of Cassie on a Segway. That's actually a standing controller. So if you've ever been like on a Segway, the way that you operate it is that you kind of like lean forward, lean backwards. I can't do it because I'll just fall off. I have no coordination at all. But you can see Cassie is very versatile. At one point, you can probably see my advisor like chasing after Cassie. It's hilarious. I love it. Next to that video, we have Digit walking around in the lab. Below that, we have Mabel running around in the circles. Where's it running to? I don't know. Next to that, that's another very dear video of mine. So like that bottom middle video, that's the very first time I was able to get a controller to work on a physical robot. So very fun milestone. And then the one next to that is Cassie walking up a slope here at Michigan. So very cool things. There's so many different controllers. And now I'm going to show you a very scary image. That. So this came from my dissertation. I am not going to go through all that. That is too much. I can literally spend hours on that, and no one has time for that. And also, it just gets to be a lot. But what I wanted to talk about was just one very specific part of this whole controller architecture where I implemented one such controller. There's actually multiple controllers happening here, but I'm just going to talk about one of them. So this one is, I'm going to use what's called a passivity-based controller, and I'll explain like why I want to use that in a second. But I wanted to show you this function. It looks different, but it's actually the same function that I just showed you like a couple of slides ago. Remember H0 minus HD? So this is the one that I used for my dissertation, and those virtual constraints that I mentioned before, I used 9 of them, and I'm going to talk about a few of those in just a second. So the controller itself, I'm going to show you another equation, looks like this. And there's not really much that interesting to point out, except for like I can say that KD, KP, these are like some user-defined parameters. You can like tune them, unimportant. What I want to talk about though is the why we like to use what's called the passivity-based controller. So you notice that there's like a D and a C, specifically a D bar and a C bar. These matrices come directly from that robot's dynamics. Remember those simple equations from before that I was like, oh, it's just like one line of code. It's not that bad, but it actually ends up being like hundreds of pages and you can like write a book on it. Those come from exactly that equation. And the cool thing about a passivity-based controller is that the fact that those matrices are incorporated in this controller, it makes it more robust. And if you want to know a little bit more about why, I'm happy to answer that in the Q&A. but I just wanted to drop that little tidbit of information. So let's talk a little bit more about the virtual constraints. So like I said, I use 9 of them. One of them I want to talk about is this pendulum length. So this one represents like one of the novel innovations within my controller. So specifically, I'm going to show you an image of Cassie, and now let me show you that inverted pendulum that I showed you a few slides ago, where it's the line between the robot's stance foot to its center of gravity. And I'll even put a dot there so I can show you like where the center of gravity is. So we have that length, and then the pendulum length is the length from that line to the robot stance foot to its center of gravity. Previous controllers would make that line stay flat. So essentially make the center of gravity height stay at a constant height. And if you're just like walking around like on flat ground, like I'm doing like right now, that's a completely fine assumption to make. But let's say you're trying to like walk upstairs. I don't have stairs here, but here, let me kind of, I'm not gonna be a mime, don't worry. I tried that career and they kicked me out. I don't know why. So if you're trying to like walk upstairs or even up like a very steep slope, that assumption, having that center of gravity height stay the same, doesn't work out. That's why, in my controller, I decided I'm gonna make that pendulum length vary. And so in my controller, I essentially like follow this type of desired trajectory, like with these arches, so it can move with the robot up the stairs or up a slope. The next set of virtual constraints that I want to point out are these ones right here. So these 3 kind of like look random, but they correspond to what's called the foot placement. And when I say foot placement, it kind of like, the meaning of it kind of like is like what the name kind of implies. So it's like exactly where I want to place my foot whenever I'm like walking. So maybe you have different reasons on like why you place your foot the way you do. Maybe you're trying to like walk faster. Maybe you're trying to walk slower. So like you'll adjust the way where you put your foot to fit whatever the desired value is. This time, I'm not going to show you equations because these ones get really crazy. So instead, I'm going to explain kind of like a little bit of the reason of like why I decided to define the foot placement the way that I do. So I talked to you a little bit about the LIP model, the linear inverted pendulum, that line from the stance foot to the center of gravity. What we want is to pick a variable that is as close as possible to the LIP model as your original model. So the reason why you use like a simplified model like the linear inverted pendulum is because you want it to be a good representation of that your actual robot. So let's look at the center of gravity velocity. Let's pick that as the key variable. So this is like a graph like what that variable looks like over time on a LIP model, which doesn't really look like anything by itself. More interestingly, let's just compare it to the Cassie model. And it's probably hard to see, but I can point it out here with these red boxes. There are discontinuities that you see on the full order Cassie model, so the actual robot, that you don't see on that simplified robot. This actually doesn't end up being like a good variable to use as a key variable. Therefore, let me look at a different variable. All right, what about angular momentum, about what we call the contact point, or the stance foot? So this is what it looks like for the simplified LIP model versus the Cassie model. And again, hard to see, but what I want to point out is that there aren't any discontinuities here. So the graphs are actually like very similar. So when I define the foot placement of the robot, I end up using this as the variable when I calculate the trajectory, or the foot placement, I should say. So lots of math. And again, I gave you like a very high level, little into the weeds stuff. I can talk more about it, but I'll say that for the Q&A, and you can also like, I guess, watch my defense if you want. But let's move on from there. So why do I personally like to work on bipedal robots? Well, for one reason, I like the way that they move. They're like very versatile. In my dissertation, I focus on like a stair climbing algorithm, and I guess I could have used like wheeled robots or robots that have like wheels, but they have trouble going upstairs. they have trouble going through mud and stuff, as you can see there. So yeah, I wanted something that is very versatile. Also, I like the coolness aspect. We can literally get these robots to walk through fire. So you can think of the applications there. What if you can send these robots out into danger while the humans are able to stay at a safe distance? So this is actually a controlled burn, like on North Campus here. You might be able to recognize those little forested areas. At one point, the robot operator, he had to step away because the smoke was getting to be a lot. But meanwhile, Cassie was just chilling there and is like, well, I'm ready to go back whenever you're ready. So you can think of the practical applications of having these robots going out into danger. Also, speaking about helping people, within the bipedal robots or two-legged robots domain, there's also prosthetics as well as exoskeletons. So you can literally get people to be able to walk again. So I really like that as an application of bipedal robots. So, and if you look at the videos, we can see that we've certainly come a long way with what we've done with bipedal robots. Look at that cool picture of a digit. It looks very majestic. This is actually on North Campus, the robotics building on North Campus. So if you haven't been to that building, would recommend it. It's gorgeous. So here are some some very fun videos that my favorite videos of Cassie. I already showed you the controlled burn. I already showed you the Segway. There's also Cassie walking on a bunch of obstacles, testing the robustness of the controller. You're going to see some videos of Cassie walking on snow, sand, gravel, on pavement. We test the Cassie walk or crouching up and down. We also test Cassie on this uneven surface. So we put Cassie's leg on one block of wood and move it up and down. And then we also get Cassie put both feet on that block of wood and have it teeter-totter. So you can see the robustness of that controller. So we've done a lot of really cool things. More cool videos of robots. We have the exoskeleton as well as the Marlowe robot on your right. You can see one of our roboticists literally kicking Marlowe to test the robustness of the controller. I would not recommend doing this to your robot at home. These are paid professionals, so don't do as they do. You can admire them, though. It's cool. Yeah. But working on robots is not all sunshine and rainbows. Sometimes we do get it wrong, as you can see from these two videos. We have two robots. The Cassie robot and the Marlowe robot, both of them trying to walk up the wayfield that is just outside of the aerospace building here on North Campus. And as you can see, they're struggling a little bit. So Cassie literally does a face plant trying to get up this ridge, and then Marlowe literally catches on fire trying to do the same thing. Yeah, you can see the camera guy just freaking out, it gets shaky. You can see him about to run towards it. It is hilarious. Yeah, so definitely still a lot of work to do, needless to say. But we do have fun. We did eventually, by the way, get up that ridge. So I wanted to point that out. I should have let that video in there. But I like showing bloopers like that. But what in the world does any of the things that I just said have to do with DEI, diversity, equity, inclusion? So far, all of it I talked about was math stuff. Seems pretty subjective or objective to me, right? Well, let's take a closer look. Let's go all the way back to that example that I seemingly forgot about that I first introduced at the beginning of this lecture. So we have Cassie trying to go from point A to point B, get to its dear old friend at the other side of Central Park. And I talked about these three domains of robotics: sensing, reasoning, and acting. So within sensing, does it matter what the robot sees and hears? Well, if you think about it, yeah, of course it does. It matters how the robot sees and hears. So you might have seen headlines like these, unfortunately, where self-driving cars were having trouble identifying kids and even people with darker skin. And in fact, there was a study right outside of Georgia Tech showing these algorithmic biases from these algorithms. unintentionally, but if we're not careful with how we program our robots, they might be able to pick up very crucial information. And I also brought up hearing too. So like, what if we had Cassie like as a voice command, like use a voice operated command? Well, it matters if Cassie can understand you. So obviously, not everyone talks like I do. I grew up in Alabama, actually. I know you can't tell from the accent. My parents both immigrated from Nigeria, and I always joke that between like their very thick Nigerian accent and the very heavy Southern accent that I was surrounded by, I got confused and just did my own thing. I'm told I sound like Midwestern, so like I think it was always destined that I'd come up here. Anyways, yeah, but bottom line, not everyone sounds like me, so it's very important that we are able to design our algorithms such that they can understand a vast amount of people. Because like even within the United States, there's so many different accents. Okay, what about reasoning? Does it matter how the robot thinks? So in this example, it's like, how does Cassie get from point A to point B? But I'm going to even broaden it up a little bit more, because like reasoning is a very big domain of robotics. So this is like just reasoning in general. How does the robot think? And it does matter. So let's look at the field of, like, for example, medicine, where they're starting to increasingly use more and more robots and AI. So I actually just came across like this headline where they're using like this AI transcription tool. So like we have the doctor and their patient talking, and then the AI transcription tool would like record the conversation and like write up a script. But then it would like hallucinate, so adding sentences and words and phrases that were not ever said. And it's doing this because of the way that the algorithm was thinking. It was like making assumptions and adding phrases that weren't said, and these phrases would often like end up playing up stereotypes, which led to like undesired outcomes in terms of like how the doctor responded to the patient when they went back to look at the transcription. And then also, like within the field of medicine, there's also well known that biases persist. So, for example, we still see to this day where patients or the doctors, medical professionals, would assume that their Black patients have a higher pain tolerance than their white counterparts. And so one wonders, what happens if you program these biases in your robots? Well, I don't actually have to necessarily think about that, because that kind of already happens if you think about robots or the tools that they use. So there's the spirometer test, which is like a way that you can measure lung capacity. And for the longest time, there was this racial adjustment that they would add to the test, where like if you're, say, like a Black patient, it would automatically assume that you have 10 to 15% less lung capacity. And there was no basis of this in like medicine or in science. And it wasn't until 2022 that they finally got rid of this adjustment. If you think about the year 2022, well, the COVID-19 pandemic hit in 2020, and it was a respiratory illness. So unfortunately, this was one of the reasons like why we saw like disproportionate outcomes to marginalized groups. So yes, it does matter how the robot reasons. Okay, what about acting? Well, you probably see where we're going with this. Yes, it does matter how the robot behaves. So again, let's bring it back to self-driving cars. So if you think about like how when you're driving your car, you see pedestrians, you see other drivers, you might communicate with them like verbally or non-verbally. So you want to make sure like if there's no one behind the wheel, so if it's self-driving, how do you convey intent to pedestrians? What if the pedestrian is, for example, blind? What if the pedestrian is somehow hearing impaired? How do you communicate intent in those circumstances? So that's an ongoing like robotics problem to think about. So all that to say, yes, it does matter how Cassie gets from point A to point B, because you don't want to accidentally hurt other people in the process of completing your robotics task. I guess the main takeaway here is that robots don't exist in a vacuum. Like, we're not building these robots and putting them out there like just to exist. They are interacting with people. So we want to make sure that we make sure those robots are interacting well. So that brings me to, diversity, equity, and inclusion. So I feel like there's been like a lot of like controversy lately in terms of like these three words. So I wanted to kind of like clear the air a little bit and like define exactly what I mean by these three terms. What exactly is diversity, equity, and inclusion? So let's start with diversity. Let's say I have a pool of qualified candidates. I'm going to pause here for a second because I think this is like one of a main point of confusion is that yes, we are considering like just qualified candidates. We're not thinking about unqualified candidates to hire for jobs. So I have a pool of qualified candidates, and I'm trying to hire them for a team to do an important task. Obviously, I can pick any one of these people, and I know that they can do the task, but I only have so many spots in my program. So how do I pick? Well, I could do what's been, like, I guess, more the norm, and it's like pick only from like one group of people. But that's not ideal, especially if I say that I value diversity within my company. So no, I don't want to exclude groups. Okay, well, what if I do this? Well, no, this is now now you're going on the other end. Now we're starting to overrepresent groups and underrepresent groups. That is not necessarily ideal, especially if I value diversity as a value. So that's not exactly what I'm going for either. So what I'm really trying to go for is something more like this, kind of like having equal representation of all of groups here. And when I think about diversity, I know there's like another misconception that we often think about just race, but diversity, of course, is a lot more than that. You're also including things like gender, disability, veteran status, age, religion, sexual orientation, and more. And I can go on a little bit about more of these. But I guess I will focus more on race in this presentation, since I'm a little bit, that's my bias, I guess. So I'll talk more about that. But yes, it's important to note that when we say diversity, we mean more than just race. And diversity isn't just relating to or is not a very new concept. In fact, we have it embedded within our government. So if you think about how the House of Representatives works, we have 435 people represent in the House of Representatives. What if we picked all 435 from one state? Let's say the state of Alabama, my home state. I'm sure they will be all very happy in Alabama. They will feel very represented. But what about the people in Michigan? I don't know if they would feel like the people in Alabama would understand uniquely Michigan issues. But that being said, of course, I don't think the people of Alabama would intentionally try to, mess up the people in Michigan. But nevertheless, the best people to understand the issues in Michigan would be the people in Michigan. Therefore, that's why we have representation from all 50 states and not just one state. So the whole value of diversity is not a necessarily new concept and doesn't necessarily have to be controversial. So that's diversity. What about equity? What is this? I'm going to root this in an example. So let's say, again, I am hiring, or I guess I've already hired. I hired 2 people, and let's say they're completing a program, a computer program that I'm working on. So one of these people already owns a computer. The other person does not. But in order for them to complete their program, or I have to say like my coding assignments, they need to be able to have access to a computer. So how do I distribute the resources that I have to these candidates? Well, maybe in the interest of fairness, I should just, I can use my resources, buy my one computer, and again, in the interest of fairness, I'm going to flip a coin and have such that each of these candidates have equal opportunity to get the coin or get the computer. And, well, what if it ends up going to the person who already owns the computer? Well, the person's like, well, thank you. I didn't need this computer. I won't use it, but thank you. Meanwhile, the other person is like, well, I don't have access to a computer. I cannot complete these coding assignments, not because I don't know how to, but because I literally don't have the resources to. All right, okay, so maybe that doesn't work out. Instead of buying one really good computer that is really good at completing the assignments, maybe I can buy 2 very cheap computers that barely work. And then just give them to both of them. So this is what equality would look like as opposed to equity. Well, the person who already owns a computer is going to be like, thank you, but I'm going to just keep using the computer that I already had because it works way better. Meanwhile, the other person is like, well, maybe they're able to finish their coding assignments, maybe it works, but they're going to be working so much harder unnecessarily. So this is not necessarily ideal either. Okay, so like, what if we just go back to buying that one good computer that I already had the resources to provide for, and just give it to this person who did not own the computer in the first place? This is what equity would be. So now the person is like, well, thank you. I can now complete the coding assignments. And again, this is important. The other person is like, cool, this doesn't affect me. I already own this computer. I can already complete the assignments. And in this scenario, everyone is happy. So this is what equity looks like. It's providing both candidates with the tools that they need to succeed. And then finally is inclusion. So I feel like this one's like the least controversial of the three, or at least probably like the more straightforward. So let's say we have like two groups, or a group of people in my company. We're trying to get them to work on an assignment. Exclusion would be like having that person or having people like reject or ignore the ideas of another person. So obviously this is not ideal. This is obviously exclusion. So we don't want this. We wouldn't want this to happen. Inclusion would be more like helping everyone would be like everyone working on the team. They were hired here for a reason. So everyone's listening to each other's ideas, and everyone feels like they're able to contribute. So feeling included as opposed to excluded. So this is what inclusion looks like. And it's also not just, or I guess like inclusion's quite broad. So you can even think about like in terms of accessibility. Let's say one of our people on our team is a wheelchair user. So ramps would be a form of like helping to include that person, so that person's able to actually get to work. And you can think of like even the language that we use. So think about like whenever you're working on a team, no one wants to feel like they're being disrespected. So being careful or being mindful of what language that you're using, such that everyone feels like they are being respected as the individual. And there's other examples too. So like you think about like parental leave, pay transparency, family restrooms, like basically all the things that like we're all humans, we all have various different needs. So no one wants to feel like their needs are like a burden to like the team or the company, especially if the team and company are able to do things to help make like life easier for that person. And there's like so much more within inclusion. So that's essentially what DEI is, diversity, equity, inclusion. Diversity is having equal representation of qualified candidates from all groups. Equity would be providing candidates with the tools that they need to succeed. And inclusion would just be making candidates feel welcome on teams. And again, I don't think any of this is necessarily controversial. So a lot of work. There's still like a lot of work to be done. So as Tim introduced earlier on, I am indeed the first Black woman to get a PhD in robotics here at Michigan, and I'm very proud of that. But as I don't think I'm the only Black woman in the entire state of Michigan capable of getting a PhD in robotics. And so I certainly hope that I don't end up being the last, but we have to be intentional about that. And if you heard or listened to my commencement speech last year, you would have heard me say a name, Kylie McMullen. Kylie McMullen is the first and only Black woman to get a PhD in computer science and engineering here at Michigan. And she graduated and finished her PhD in 2012. There has not been another Black woman before or after her to get a PhD in computer science and engineering. And again, I don't think that she is the only Black woman in the entire state of Michigan capable of getting a PhD in computer science and engineering. So one has to think about, okay, if we're not graduating like a diverse group of people, what is needed to overcome those barriers? And again, I'm sorry, I'm picking on Michigan here. I promise I'm doing this out of love. And I also appreciate that these numbers are actually being made public. I think one of the most important steps of being able to fix these challenges is to be able to get data. And the fact that we do provide this data is very, very key to that, so I appreciate that. So I took the College of Engineering's population, the enrollment numbers for the University of Michigan for in this last fall, and this is what the distribution looks like in the undergraduate and graduate realm. And it's a pretty similar distribution between the undergraduate and graduate. So let's just focus on the undergraduate and compare this to the Michigan 2020 census. So as you can see, there are discrepancies between the entire state of Michigan versus the University of Michigan population. And so one would want to consider, if this is a public institution, we want to make sure that we are serving the public that we are, we want to serve the public that, sorry, I am confusing my words. But yes, serve the public essentially, because it's for a public institution. Sorry, I woke up at 2:30 a.m. to catch a flight here, and I think the sleeping is hitting. So bear with me, it's okay. But again, why do we care about any of this again? Well, it goes back to the example that I started this lecture with how robots sense, how they reason, how they act. It matters how the robot sees its environment. It matters how the robot thinks through problems. It matters how the robot acts as well. But the robot's ability to do good for all of humanity is dependent on the team of roboticists that actually make the robot. And it's too big of a question, too big of an ask for any one person to understand the all of humanity. It's okay that we have these differences. It's what makes us humans. It's what makes us great. But to help us and make up for each other's blind spots, it's good to have a team of diverse perspectives such that we can pick up or see the things that maybe our own individual experiences cannot see. In fact, I have a quick anecdote on this. So I remember when I first went to my college in undergrad, so now I'm picking on Illinois. Again, I love my alma maters. I'm sorry I'm picking on them. But it was the first time I was interacting and talking to friends where they were, I was the first black person that they ever interacted with or had a meaningful interaction with. And these, again, very lovely people, amazing people. They were my friends, obviously. They still are my friends. But I realized that this wasn't a unique experience. It's very common that we might grow up with only surrounded by a very same group of people. And so one would hope that when you go to college that maybe you're able to diversify your perspectives, but as we saw in the previous slide, this is not necessarily happening either. So you can kind of see how this trajectory happens. You can grow up with the same group of people, graduate with the same group of people in college, and then go up into the workforce, and then inadvertently, accidentally make algorithms not considering other groups of people. So I don't think that any of the people or the roboticists that I talk to, that they intentionally try to make algorithms that are biased and harmful to groups of people. It's just those perspectives. Your experience is fueled by your own perspectives. So this is why you want to have as many different types of people as possible on your teams. So where do we go from here? Well, actually, I gave a talk about the answer to this very question. So, in fact, you can check out my TED Talk on how to prevent the robot apocalypse. So when I said robot apocalypse, I was referring to essentially exactly what I was hinting at before, how to sorry. Oh wow, I do really need to leave. I'm so sorry, guys. How to prevent the I gave a talk gave an answer to this exact same question of essentially how do you prevent the robots from inadvertently harming groups of people. And I'm going to do a very tacky thing here, and I'm going to quote myself, so bear with me. The answer that I gave was that as we build the future, we must remember that our technology reflects our values. So let's make sure those values are rooted in empathy, diversity, and a deep respect for humanity. And in fact, this is exactly what diversity, equity, and inclusion work aims to do in its best form. So, okay, what am I doing to help this? So obviously, I've been just lecturing at you guys, but what am I doing to help alleviate this challenge? Well, I'm currently a professor, and that was very intentional. I knew that when I was going through college that I wanted to be able to help teach and mentor the next generation of engineers. So I'm currently serving at Rose-Hulman Institute of Technology. I love it there. I'm about to join the Ohio Northern University campus. Very excited about that. And so in my future or my academic work, I'm working on this biped boot camp, or I had developed this biped boot camp during my PhD experience, and I mentored a lot of amazing undergraduate students. In fact, I see a couple of them in the audience. One of those students is helping me convert that to a series of courses for undergraduate, so that's Ankita, and the idea here, the goal here is that I noticed when I was going through my grad school that the programs that I was working on, it was only accessible to the graduate students. And I was thinking, I could have totally learned this in undergrad, actually. So that is the idea behind the undergrad courses that I want to make. And of course, still making cool controllers, so making robots do cool things. And I want to, again, make this accessible to undergraduate students. So that's why, again, teaching or towards the undergraduate or developing those undergraduate courses. And okay, so I added these slides very last minute. In fact, I added them last night, and I think it was more of a silent protest. So I don't even know exactly necessarily what I wanted to say here, but except that I've been hearing a lot of this rhetoric of DEI being mutually exclusive from merit, and I think that's just couldn't be anything further from the truth. And in fact, this idea is not necessarily new. I've been hearing it all my life. And so I remember going through undergrad, finishing my degree, and then applying to grad schools, and then having people come up to me and tell me that, well, you of course could get into any graduate program that you want because you're a black woman. And it's frustrating to hear that. And so especially when I think about what I did in my undergrad to get there. So in undergrad, I spent 4 years, and I finished the mechanical engineering, a Bachelor of Science in Mechanical Engineering with honors, and completed a TEF Technology and Management program, or minor. I completed an engineering co-op. I visited 8 different countries. One of those was a research abroad experience. So my very first research experience. 2 of those were for a competition where I was able to win first and third place respectively in those international competitions. Went to 23 different cities. Some of those were conferences. Some of those were corporate site visits for the business trip that I was on. Got 9 different scholarships, 9 different awards, 9 leadership positions, 3 teaching positions, wrote a second book. Yes, I did a first book back in high school, and then so much more. So having gone through all of that in 4 years, and then hearing that rhetoric of saying that you're only going to get into where you want to go into because you're a black woman, it's very frustrating to hear, but again, it's not new. And again, thinking about what I did in grad school. So 6.5 years, but my PhD in robotics was specifically, that was 3.5 years, so I started in 2020, right in the middle of the pandemic, so my entire PhD in robotics was during the pandemic, and was able to complete 3 conference papers, 3 peer-reviewed abstracts, 10 fellowships, I had 8 undergrad and grad mentees, wonderful, amazing people, held 5 leadership positions, did 13 plus outreach events, 2 teaching positions, got a perfect 100% on one of my grad courses, where I was able to actually act as an impromptu TA. So I noticed that the teacher needed some help teaching my fellow grad students, because it was like one course and a bunch of us. So I took it upon myself to hold my own office hours, even as I was like learning the course in itself. And did so much more. So again, I think when we hear this rhetoric of like DEI, having like these DEI hires, and that being like a kind of like a implying that somehow these people are not merit or don't have the merit, I think that is very harmful language and can be very frustrating for people like me who work very hard to get where we're at. And again, think about like when I was talking about diversity, we are considering only these qualified candidates. So again, I would like to, I guess, end the talk here. Sorry for like getting the roughness towards the end. Next time, I'll remember to plan more time when traveling to have a day to like sleep in a little bit. You live and you learn, right? Actually, we just finished at the end of our quarter yesterday too. So like I just finished like a class and then like hopped on a plane. But I want to thank a couple of people here. So a lot of the cool videos that you saw was from my PhD lab, and you can see more of those videos in the Dynamic Locomotion YouTube page. And again, I wanted to also give a huge thank you to the Michigan Robotics Department, who continues to support me. And I really love the slogan that they have, the robotics with respect. That's exactly the type of mindset, the type of foundation that we need in order to build robots for all of humanity. And with all of that, I would like to thank you for your kind attention, and I can take your questions now.
Well, thanks so much, Wami.
Thank you.
It was really interesting. It was really exciting and quite challenging. So I think we all appreciate that. So we would like to entertain. We'd like to have you ask questions of Wami. We have some questions that have come on online, and we invite those online to continue. You can send them here, and I'll get them on my phone as they come in. So we have microphones set up here. Let's see if we can start with people. We're not going to manage this too much. Do you think we should take kind of both categories of questions simultaneously, interleaved?
I think that's perfect. Yeah.
Okay, very good.
Mix it up.
All right, you're first.
I have two quick questions.
Yeah, please get close to the microphone for us.
So, question one, the center of gravity being set at a constant height above the ground seems like a non-obvious choice. How the heck did that happen? Because people don't walk that way. That's why robots look funny when they walk, seems to be.
Yeah.
And the other one is there have been a lot of improvements in robot technology in the last few years. Has that been, do you think, mostly due to improved ability to get computers in small spaces, or an improvement in the math, in the model? Is it like one or the other, or is it both? Those are my questions.
What was that? That other choice that you said? She said like improvement
in the mathematics and the modeling of what you're trying to do, or is it that the computer can now implement the strategy of movement better because the computers are just smaller and more powerful?
Yeah, I would say actually, so I'll answer that second question first. So like, what has been contributing to the improvement of like robotics in general? Is it the improvement of like the algorithms that we use, or like even like I guess like the computers themselves they're on? I would say like it's a combination of both, certainly. So like, I'm trying to think of some examples, but like. Yeah, so like the algorithms that we're developing become increasingly more and more complex. And it's the computing power needed to solve these algorithms becomes very like important and very high. So like there's like this kind of like neck and neck like race and like the improvement of the way that we design the algorithms and the computers that we put them on. And as for the first question, which I believe you're asking about, like why in the world did people have that assumption of like having that center of gravity be constant when you're walking? And I think this is I can answer this with like a little joke of why mathematicians really do not like engineers that much. It's because we like to make all these assumptions. In this case, we made the assumption that center of gravity is constant. Now the engineers that were making it, they knew that it wasn't constant, but they were it's constant enough, it's close enough that we can make the assumption it's constant. And engineers, we do that a lot. We will look at something and put an assumption around it. And then if the factor of safety is high enough, it's fine, right? But yeah, it was just because it worked well enough. And if you're walking on flat ground, the assumption holds really well. Yep, good questions.
Don't be bashful, those here. We're on the technical issues. One question is, could robots ever run? But you actually showed a robot running, however, it was tethered. So,
yes.
Can robots run, or will they ever be able to run?
Great question. Can robots run? In fact, yes, they can. I didn't show a video, but we did have a video of Cassie. This was a different lab out in, I want to say, Oregon State University, I think, might have done this. But yes, they were able to get the Cassie robot, which is, I guess it's not in that picture, but the other robot that I showed you, they were able to get it to run, I think they even did a 100 dash, and it was really cool, and also pretty spooky. I don't know, seeing these robots run is very, I don't know, it feels very awkward. We need to work on the, more controller design, but it is really good, yeah.
I once actually advised a student who was working on an undergraduate thesis on running, the physics of running, and it turns out we don't get it. We don't understand how people can run. I don't know if that's changed, but so that's follows on this question of can robots run. Another one, this is an interesting question. Is human walking not optimal? If you're making robots walk this way, very different from humans, is there something wrong with what we do?
I guess what do you mean by non-optimal?
Could we do better?
Could we do better? That's a good question, and I feel like that's a question more for a biologist. If you ask me could robots run better, I would actually say yes, and that's just in the algorithmic design. But from a human perspective, that's a good question. How do humans run?
How do
humans run?
Oh, how do humans run?
Yeah.
Well, as I said,
we're still trying to figure that out, right?
And I still don't know.
Or, yeah.
Okay.
Okay. I have an engineering question and then a diversity question.
Yes, absolutely.
So, do you think the work on bipedal robots, and this kind of goes to what you guys were just discussing, does that show a bias in the fact that humans are one of the few mammals, one of the few animals on the planet who walk upright, right? Apes do to some extent, right? But they also use their arms. Does this work show any sort of bias towards just our own humanity?
Oh, yeah, you bring up a very interesting point. So the robot that we brought up here is Digit, and you can see it's falls in the category of these humanoid robots. So they're designed more towards us. But who's to say that this is the optimal robot shape? And actually, roboticists have been thinking about the answer to this very question. So there aren't just humanoid robots. We also do four-legged robots. I've seen robots I know there's within the category of drones. Instead of having the quadricopters, what if you modeled those robots after birds, bird wings, and stuff like that? It's an ongoing field of study. In fact, this whole field of bio-inspired design. I guess the answer to that question is that we're still trying to figure out, and it depends on what type of task that you're trying to solve. So, for example, I can think of the Digit robot, what they're using it for. They have it currently working in these warehouse spaces where they're trying to pick and move tote boxes, and so a robot of its design ends up being the ideal robot for that task. Yeah.
And so my diversity question is, what can we do to encourage diversity in companies? You talk about cars, autonomous cars, and blind people. Car companies have not really had to hire blind people, right? Or they've not thought about hiring blind people because blind people don't drive, right? So what is it that we can do to kind of encourage that diversity of thinking?
Yeah, I think we just have to like be more, just like be intentional. So like in terms of if we go with the self-driving car company, if we can find like the engineers who are blind, or even engineers who are connected with the blind community in some way, like any way that we can like incorporate those perspectives, and there's different ways that we can accomplish that task. Yeah, does that answer your question? Okay.
Over here.
Good question.
Yeah, so first of all, I just wanted to say it's nice to see you again, Wami.
It's great to see you, yeah.
Yeah, we missed you in the lab. No, it's been great. Wami was super helpful. It was like very formative to like the research I did, and it became, like I owe a lot to her.
Thank you.
On that note, I just had like a question about diversity, because like you, I care a lot about, especially with recent times, the changing landscape. As like an East Asian guy, we saw the graphs with the representation and how it should be, right? I can sit here and I can logically understand that, we should be representing everyone proportionally, right? That is like my logical sort of take on the matter. But emotionally, as like a individual, right? When I apply that logic, I mean, we saw like the graphs of the Michigan population versus students. Emotionally, the logical notion that basically we should be taking less like East Asians in order to actually give more space to other people, it makes sense, but it's hard to sort of combat like the human innate selfishness that I often have, like the emotional part on this matter. I like to think of it as like the goober part of me sort of battling with like the logical version of me where I'm sort of at odds, And I feel like this innate selfishness is kind of a huge issue in like why modern DEI is controversial, even though it really isn't, And that's why like so many actors or like proponents or people who like try and strike down DEI, a lot of them are acting in bad faith because I feel like they're just trying to cover up for that innate selfishness, right? But selfishness itself is a pretty human concept, right? It's pretty, like, as someone who did reinforcement learning stuff based on the work you did, selfishness in like evolution has been advantageous, but now it's like very clearly working against us, So I guess, what are your opinions on this whole DEI debacle being tied to like a more greater issue that is like ultimately an issue with being human, being like an emotional creature?
Yeah, absolutely. I think that's a very, very good and valid question. And thank you for bringing it up. And like you, I have like that same like we're only human, right? And I wish I had the answers, but I do not have the answers to this question. From like the perspectives that I was bringing. In terms of whenever I hear see the rhetoric, and there seems to be like an assumption that like we're like taking spots from people and giving them to others, and it's like I guess it depends on like how you view the scenario. So. Bringing back, to my perspective, like me being like the first, currently the only Black woman to get a PhD in robotics at Michigan, and thinking like I can't be the only one. I wish there's not really an eloquent way of saying this, and I think the solution is just like an ongoing this is like the lack of sleep also too.
Yeah, my apologies for that.
No,
like,
I
get what you mean. Yeah.
Yeah, no, it is a very good question. I think another important thing is that like I don't want this to feel like we have to like pit groups against each other. I think that is also like a very very unhelpful thing. And I think we have to think about like what are our goals? Is our goals to help make sure that I guess in the context of like like these self-driving cars, like we continue to see like these biases. Like how do we resolve those? How do we diversify the workforce? Do we have enough good incoming talent? Then like, okay, let's look at the colleges. Do we have, are they producing enough of these good diversified talent? And the question, or I guess the solution, it ends up being like very complicated, and we have to like, there's a lot of good factors that we have to consider. So I know like that's not really, that's like very much like a non-answer, but yeah, we have to, it's complicated.
Yeah, I mean, ultimately, it is like a really difficult problem, right? Especially considering when you have to factor in the fact that pitting groups against each other makes a lot of money for a bunch of social media companies sometimes, right? So there's that whole debacle. But yeah, I just want to say ultimately, like, I definitely agree with you. With modern robotics, we're like, what we do in the lab, like what I do specifically, reinforcement learning, we're like trying to emulate like artificial life, So we need to, DEI sort of brings everything, DEI is sort of a way to correct worldviews, to bring it up to like an objective baseline, right? And why wouldn't you want that if we're trying to make, literal artificial intelligences? Why wouldn't you want them to be as unbiased and like God's eye view, as like God's eye view as possible, So I really appreciate everything you've done for us, done for Michigan. So yeah, thank you.
Yeah, thank you. Appreciate it.
I was going to add something, I won't, but yes, absolutely.
Oh, thanks.
But I do want to say, just now, in the midst of our Q&A, because it will go on, but thank you for bringing both these topics. They're both extremely important and appropriate for Saturday morning physics, and as I said, challenging. I'm not a dispassionate moderator, but I'm going to go to the next question from the audience.
Thank you. My question is two parts to it. The first one is in regards to two great graduates that came from the University of Michigan, Daniel Kahneman and Amos Tversky, who wrote a lot about the flaws in human judgment and behavior. So that question is do you really think that the technology is way too far ahead in terms of that? There's a gap between that and what we really know about human behavior, and that's related to those policing algorithms that people talk about a lot. But the second part of my question is, I am a substitute teacher in my retirement for the high schools in the Plymouth-Canton area, and this is a question that came from them, and it's called, in regards to equity, when you look at a student versus student athlete, where currently students are in angst and they're emotional in terms of going into debt for college. And then they read about an athlete who gets $10 million as a freshman to go to the University of Michigan. Where's the D&I? I've called the Department of Justice. I've talked to the University of Detroit Mercy. I've talked to the University of Michigan. I don't see anybody approaching that topic in terms of, okay, so I got one student that's going to be going into debt and another student that's going to go to school in a BMW. I'd just like your opinion on that, but the first one in regards to technology being way ahead of the decision making.
Yeah, can you actually repeat that first question again?
Where the technology seems to be way far ahead in terms of our science of human behavior and flaws.
Okay.
Because, I mean, if we humans have still a ways to go in terms of, of our judgments, which, they wrote the two books. One is the Noise, and the other one is the Think Fast, Think Slow. And you can see in there where, we have a lot of pitfalls in terms of our judgments and some of our decisions. So it's almost like the algorithms are going to have to take into consideration at this point, policing is going to be difficult.
I think that that's actually kind of like it's one of the reasons why humans are such like a great species is that like I feel like it's our fatal flaw, but it's also like one of our greatest traits that we like to bite off more than we can chew. But I think that's exactly like where like innovation can happen, where we continue to try and test out and build these cool new algorithms, these cool new robots, and then they do fail, but then we learn a lot from that failure. So like I guess, yeah, in the context of this whole DEI stuff, in terms of like we're building these robots and we see these negative outcomes, okay, how can we like not keep doing those negative things? How do we resolve those? So as long as like, it's okay to like, I guess like bite off more than we chew. It's okay to like keep, to do these like cool things as long as we learn from those failures. So that was the first question. And then the second question was?
Was the equity issue on student versus student athlete?
Yeah. Sorry, were you going to say a comment?
Oh, I was just going to actually say maybe we could discuss that at the end.
Okay.
And then I wanted to have a couple of technical questions from online.
Okay, sure.
If I could.
Yeah, okay, we'll talk
But
offline.
we won't forget your question. So one of them,
Oh man, it's just like the Oscars, I get like played out. I was talking too much, I'm sorry guys.
so these are pretty technical, but neat. So how many frames per second, I guess, would be a way of asking, or decisions per second
Interesting.
need to be made by a robot? And how does this compare, do you think, to humans, where I think it's, it's like in the tens of milliseconds? So.
Oh, that's a good question. Yeah, so
Cores
like,
per second.
yeah, so I guess and we have a technical term here for roboticists. It's the execution time of your algorithms, and the answer to that is, you're not going to like it. It depends on what you want to do. So like at the very cutting edge of robotics, you'll see we have like I'm thinking of an example of like some of my friends who work on these manipulation robots, and they like be solving like these really big complicated problems and like use like big machine learning algorithms to solve these problems. But the thing is, it will take very long to do those computations, and if you don't, I guess, care about like how long it takes, then you can do these like bigger problems. But in the case of like if you are more like time sensitive, then the ability or what you can do in terms of like complexity of the problem that you're trying to solve, you might have to like think about a little bit more about like reducing the complexity. So long story short, for walking robots, the I guess like the speed at which we're making decisions is, I can even give a unit. It's 2 kilohertz, which I know that's not going to mean a lot to the non-roboticists in the room, but that's really, really fast, essentially.
I get it.
Yeah.
Half a millisecond, right?
Yeah.
500 microseconds. Yeah. All right, and the other one is, this is mathematical, but so you have a 5-dimensional, 5 degree of freedom in your robot. Does the, sort of like the matrix, right? Mathematics of that. If you went to 6 dimensions, would it just be 20% more, or would it grow exponentially?
Oh, that's a good question. Yeah, because like I guess you can kind of see like that was like happening with like the robot equations that I was showing. Yeah, it does kind of grow. I don't know. Okay, I guess I'm being very precise here. I don't know if it's necessarily exponentially, but yes, it does very much increase in complexity the more degrees of freedom you have. Yep.
Great.
In the book Live Wired, they talk about how biological forms sort of aren't pre-programmed with how to move, but the brain kind of figures it out, and that's what childhood is about. And thinking about both the complexity of some of the matrices that you had up on the screen in terms of actually programming an algorithm for robot, hey, do this, versus the up-and-coming AI where it's sort of machine learning. I'm wondering where you see that race playing out. Is it worthwhile making more and more complicated algorithms, or is the way forward really having AIs that kind of, oh, here's a new leg, let me figure out how this leg works. Oh, we're going to upgrade your legs, I'll take it off, let's try it with, now you've got twice as many actuators. but you, robot, you figure it out. Like, where do you see that coming out?
So you're asking, like, should we, like, design for the algorithm, or should the algorithm design for the robot? Is that what I'm hearing?
Do you see the long-term future of robotics being sort of an algorithm deterministic system, or do you see sort of the machine learning being more the way forward?
It's a very interesting question. I think it's more confusing, or I guess I'm not sure if I quite understand the question.
I think he's asking like the classical control theory, like the model predicts itself, versus like the end-to-end reinforcement learning. And the truth is that we need both, right?
Yeah. Yeah, so I think there is definitely like a lot of potential, and like certainly we see like a lot of applications within like like machine learning. I'm very, I guess like one thing, one piece of innovation that we would probably want to see is that we know that like these big machine learning algorithms, they take a lot of like processing power, and it's like very, in terms of like, I guess like energy and efficiency, it's like it's a lot. So I think that we have to like in order to keep proceeding down that path, we'll need to like have more innovation in terms of like even the computers that we're building that are like processing the algorithms, because like I think there is like a ceiling like at this current trajectory, but that's my personal opinion. Yep.
Thank you. I very much appreciate your including the DEI in a physics lecture. I have a comment that regards to the, in terms of self-driving cars, for instance. Well, you're not going to have a blind engineer because they don't drive cars. I have a blind brother who's very dependent on the blind input, because when cars went hybrid and are silent, he can't know they're there.
Yep.
That's the kind of thing that you need more representation, whatever you're doing. A bigger question that probably doesn't have an answer is that it seems to me, as a non-physicist, all of the models, all of the robotics, all of the computerization is very math-oriented. It's very concrete, which limits it for a lot of the human applications that we really need. And I don't know how to bridge that gap when you get the question of, well, are computers just too far ahead of humans? I don't think it's an ahead behind. Humans need value, make value judgments all the time. Do you see a way that can be bridged with computers?
Yeah.
I mean, you can't program in values because that's very biased.
Are you asking about like okay, I think I originally misunderstood your question. So you're not asking about like the accessibility of like having people be able to work with the robots. You're more.
I jumped.
Okay.
From one to the other.
Yeah.
Because I don't think we can. If we base everything on, there's a real appeal to making everything accurate and repeatable, and that's very appealing to people. We know what's happening. But that's not really how life works. And we're seeing that with the climate control, and we're seeing that, we didn't consider that factor. So it seems to me that you're, by definition, building bias into all of the computer programs because we can't possibly include all the necessary factors.
Oh, sure, yeah, that's fair. So like this goes into like why we try to make those teams as diverse as possible, because like it's what makes us human, right? We are all like very different, and that's great. The challenges grow when we start to only like incorporate like only like a few perspectives. So if the more that we can include, like the more I guess like ideas, perspectives that we can include, the more I guess we can account for in terms of like making sure these robots have as a little bias as possible. But I agree, it's not, it's probably like it's a problem that we can never like completely solve, because like at the end of the day, we are humans, we're building these robots, our biases are always going to be poured into these robots. The only thing that we can necessarily do is like try to reduce the bias as much as possible, but that requires some intentionality in terms of like how we build the teams and the people that are working on the robots. Yeah.
So in machine learning, there is a concept of bio-inspiration, that people really study how the brain works, how neurons function. They try to build hardware analogs. They create neural networks. But eventually there's a kind of realization that bio-inspiration and biomimicry are two different things, and that while it's useful to take inspiration from biology, it's not necessarily the best answer in every case. I'm wondering how much of that there is in robotics. I hear about people making robots like humans, like snakes, like birds. But at what point do you hit the kind of limitations of the bio-inspiration?
Yeah. I mean, like, I think one of the reasons why we like robotics in the field of bio-inspiration like it so much is because, like, I mean, I guess, like, evolution ends up being, like, a really good, like, I don't know, the word that came to mind was teacher. That's not the word I'm looking for. But nature does solves problems really well, so it's a really good starting point. But yeah, I think I get like what you're trying like alluding to, or like I think there's definitely a possibility in terms of like is there a way that we can somehow do better than nature? The answer is I don't know. So far, I think the answer, what people are thinking like right now, is that nature is doing it pretty well right now. So that's the one that we're trying to like mimic.
I guess like as I asked, I realized that our most successful small drones have rotors instead of wings. So that's maybe an example. Okay, thank you.
Oh, yeah. Good question.
I just want to say kudos to you for getting your PhD.
Thank
And
you.
then also as well, I want to ask two separate questions. First one in regards to equitable innovation and I guess encouraging innovation in our country that's primarily driven by our social human dynamic of profit. And also just agreeing with what this gentleman said right here in regards to our competitive nature of resource hoarding and along those lines, how do we ensure for our next few generations that we are encouraging that we use innovation in a sustainable way to encourage equitable innovation? And how do we prove these things on a quantitative, objective measure rather than profit?
Yeah, so that's a very good question, and I think it ends up going down to like the policies that we create, because like I think within our current system, it's not necessarily like I guess rewarded to have the necessarily the most equitable solutions. So if we do care about like these other values, we have to make sure that we I guess like design our policies such that these are like what we have to like guideline. Like this is the bar that we have to reach, and then anything beyond that, great. But we have to make sure that we're at least reaching these bars.
And then how can we prove that it's also a good thing that we do this? How can we show that these measures are also things that we should encourage? But that's not the second part of my question. My other question also has to deal with nowadays with funding for public education for K through 12 education. I'm hearing a lot of sources, I don't know how true it is, that a lot of these things are considering to be gutted. And for underprivileged students, especially students who don't have access to these resources or who may not consider any of these things on a daily basis because it's not encouraged in their immediate community, or they don't have access to these things in their immediate community to prioritize some of these subjects and the funding to get access to some of these subjects. How do we ensure that we can, on our own, I guess like U of M does a great job at doing this too, but for companies and private places who want to see sustainability and equity, how do we ensure that they're reaching out to areas that aren't receiving as much funding for young students to be the next PhD students in Michigan?
That's a great question. Yeah. And I think to answer like the first part of the question in terms of like how do we like make sure like it's rewarded that like when we that these goals are these diversity, equity, inclusion goals are like good and are rewarded. I think so. I guess this goes back to like our human nature. So like another one thing that I think is like a good trait of us is that I don't think, I think it's our intention that we have this natural inclination to like help and want to help and support one another. Like we're very community, social oriented species. So I feel like that drive, that reward can be innate within us. And as for the, I guess, later part of your question in terms of like, how do we, I guess, disseminate resources? Well, I think it goes back to policies, programs, and I like some of the things that we're doing here. Even here at Michigan, there are these like outreach programs that are intentionally going out towards communities that are not that don't have as many resources. So keep doing that, and don't take away funding from that, please, because like yeah, the potential is there. These potential students who have these capabilities are there. We just have to be intentional in terms of like reaching out and providing the support. That's the equity aspect of it. Because certainly there's a lot of people out there who also have like abundance of resources and are able to will definitely like be on that path to succeed. But it's also, we have to be intentional in terms of like looking at these other communities that may not have as many resources, providing those resources so that they can also reach success. Yeah.
Thank you.
Thank you. Yeah.
So let's finish up. I'm going to try to bundle several questions that have come online and follow a little bit on Gabri's question, which has to do with racial bias. And we had our last Saturday morning physics of the fall was on artificial intelligence. And it was pointed out that the using cameras to try to find crime suspects is apparently significantly racially biased and kind of picks the darker skinned people more often and more often innocent people. But racial bias research, this is legitimate research, differences in diseases and so on, which seems extremely relevant, but also extremely in danger currently. So I wonder if you could sort of apply that to aspects, as Gabri's kind of asked, of aspects of your research, and also how you feel your funding prospects are, given that this is also like a really important the future of technology, and how can you not support the future of really important technologies?
Oh, certainly, yeah. And like this is something like I guess that is very much at the forefront of my mind. You know, like about to start a new position, and like now having to considering like, okay, where am I going to get funding sources? And then it's complicated. Yeah. I think there's still avenues, because like the problems that we're trying to solve are still problems that are beneficial for like everyone. So like in terms of like my personal research, I'm doing like specific controllers on bipedal robots. There's like wide applications on that. So I think there's still plenty of funding opportunities to support that research. Probably being careful in the way I word the proposals is important. Yeah. It is what it is.
It is what it is. And we will succeed.
Yes, absolutely.
Okay. Well, thanks, Wami.
Thank you for having me.
And thanks, everyone.